I tell you, let's say I flip a coin. What's the probability that that coin would be heads? Yeah, 1 and 2, 50%, right? Okay, let's say I flip a coin. What's the probability that the next coin will be will be heads? 1 of 2, right? They're mutually exclusive. They're independent. The second coin doesn't know what the first coin did, right? So they're just completely independent. Okay, now is there any possibility on any single toss? Is there a possibility other than heads or tails? No, right? I mean, short of it's landing on the edge or something like that, it's going to be heads or tails, right? So chances of it being heads is 50%. Chances of it being tails is 50%. There's no other possibility, right? So that's exhaustive. If I add together the possibility, there's only 2 possibilities. If I add them together, what are they going to add up to? 100%, right? Or 1. If I look at it, it's 0.5 and 0.5, it adds up. So we have this idea of independence. One event doesn't affect the other event. And we have this idea that we can add these probabilities together if they are mutually exclusive, right? One doesn't affect the other. And that, and sometimes they'll be exhaustive. They'll add up to 1. Okay, so let's take an example. Let's say I tell you that in this given population, that the probability of someone being insured is 80%, right? So if I picked one person on the street completely randomly, what would be the probability that that person would be insured? 80%. What's the probability that they wouldn't be insured? 20%, right? Because they're either insured or not insured. Okay, now let's say I picked 3 people out randomly from this population. What's the probability that all 3 would be insured? 0.8 times 0.8 times 0.8. Just like with a coin, when we looked at a coin, right? The probability at the first, we had a couple of possibilities here, right? We could have heads or tails, right? And once we toss that coin, if it's heads, there's an equal probability the next toss could be heads, or the next toss could be tails. If it came up tails, it could be heads or could be tails as well, right? So the probability that we would get, I'm going to get back to this in a second. Probability, if this 80% is the probability of one person being insured, probability of 2 people being insured is 80% times 80%, 0.8 times 0.8. 3 people being insured is 0.8 times 0.8 times 0.8. Now, anybody know what that is? What does that come out to be? Anybody? Any 0.8, 0.64, right? One of you guys have a calculator? Don't make me do it in my head, please. 0.512. Okay, they beat you to it online. Okay, 51.2% or 0.5. What's the probability of if you randomly select 3 people and assuming you randomly select them and each choice is independent, so you've randomly selected, what's the probability that 3 people out of 3 people would be uninsured? Bingo, exactly right. Okay, anybody want to figure that out without having to multiply that out? It's the other possibility, right? So 0.2 times 0.2 times 0.2, what do we get there? What do I get? 0.03. Okay, that's close enough. All right, so now let's say that I told you that we took 3 randomly selected people. We did many trials of it. We did this many times, took many trials, and we averaged them. And we know that the population average is 80% insured, right? Let's say I took 3 people and 3 people and 3 people and ran this test. And I found at the end that the probability of all 3 of them being insured turns out to be 60%. What could you tell me about that, my initial assumptions? Why might that probability be higher than what I would have expected it to be? Maybe they're not independent, right? For instance, I'm talking about insurance. If I pick 3 people randomly, maybe my random selection is not really all that random. If I picked them off the street as they walked by, well, maybe I was occasionally picking a married couple. If they're married, they're more likely to be more likely than 80% to be both insured, right? Because most people have insurance through work, and then they wind up with their spouse being insured also. So if I get something other than this result, it would suggest that it's really not an independent selection. But if it's independent, then this should work. Okay, so let's take a look at one of these other examples. Let me get back here to this. Okay, of course, you pick 10 people randomly from a population, probability of 10 are insured. It's going to be 0.8 times 0.8, and so on. 0.8 to the 10th power. Okay, probably you choose 3, and we're not randomly sure. We talked about that. And this we talked about as well. You did this 1,000 times, and we found that maybe it wasn't independent. That's a good test to see if it's independent or not. Okay, I'm going to open up this next file. Okay, so now I'm going to look at this idea of the number of ways that we can have different outcomes. So I'm going to take that coin toss that we were just looking at, and I'm going to examine what happens if I toss a coin twice, right? If I toss a coin twice, right, the first coin has got to be either heads or tails. Second coin, if the first coin was heads, the second coin is going to be either heads or tails. If I and again, if it had come up tails, the second toss would have been heads or tails. So how many ways do I have that I can get 2 heads? Well, both of them have to be heads, right? So there's only one way here I can get heads. So if the probability of being heads is 0.5, probability of being heads again is 0.5, what's the probability of getting 2 heads in a row? Right? What's that probability? 0.25, right? 0.5 times 0.5. What's the probability of getting exactly 2 tails in a row? 0.5 times 0.5 is 0.25, right? So now what are the other possibilities? Well, the other possibilities is the first coin could have been heads, second coin could have been tails, right? Well, a 50% chance of getting heads, 50% chance of getting tails. The chances of getting 1 head and 1 tail was 0.25. What about the probability of getting a tail first and head second? 0.5, 0.5. That's also 1 head and 1 tail, and that's 0.25. So what's the most likely outcome for me if I flip 2 coins? Well, how many ways do I have of getting 2 heads? 25% of the time. What percentage of the time do I get 2 tails? 25% of the times. What percentage of the time do I get a head and a tail? 50% of the time, right? Because there's more ways to get it. What are these going to add up to if those represent all of the possibilities? 100%, right? Okay, everybody comfortable with that so far? All right. So now let me extend that a little bit further. Let's take that out. I'm not going to bother to take it out to the next level. If I do it with that, well, actually I will. I'm going to make it a little bit more interesting. Okay, this time I'm going to discuss, let's say that you take an exam, a multiple choice exam. Okay, and when you take that multiple choice exam, there's 5 random selections. There's 5, it's like A, B, C, the answers you can give A, B, C, D, and E. Okay, now let's say that there are 2 questions on this exam. Okay, so when you take the first question, you can either get that correct or you can get it incorrect. Okay, so let's say you can get it correct or you can get it incorrect. What's the probability that you'll get the first question correct? Right? What do you think if you didn't know anything about it? Right? One chance out of 5. What's that? 20%, right? 1 out of 5. What's the probability you're going to get it incorrect? It's going to be 80%, right? Because there's only 2 possibilities, right? They're exhaustive. You either get it right or wrong. Does this make sense to you guys? You getting where I'm going with this? Okay, so now what about the second question? Okay, assuming you got the first question correct, what's the probability of getting the second question correct? It's also 0.2. Again, you don't know anything about the question, right? And what's the probability of getting it incorrect? 0.8. Okay, so that would be if we get it incorrect. Okay, now if we got the first one correct, we have the same probabilities. There's 20% chance of getting it correct, and 80% chance of getting it incorrect. Okay, so now what's the probability that you're going to get two of these answers correct? Well, let's take a look at all the outcomes that we could have, right? We could be correct and we could be correct. Both, we can be correct on the first question, correct on the second question. So what's the probability that we get two right? Two correct, right? What is that? 20% for the first time, 20% for the second time. So what's the probability? 0.2 times 0.2, right? Is going to be what? Right? 0.04, am I right? Right? 4%. What's the probability that you'll be wrong both times? Right? What's that going to be? 0.8 times 0.8 is what? 0.64, right? That's two incorrect answers. So now what are the other possibilities? You could get the first answer correct, second answer incorrect, right? So that's one correct, one incorrect. Okay, you could get the first answer incorrect, the second answer correct, right? These are really the same, right? One correct answer, one incorrect answer, right? What's the probability of that occurring? Right? Well, I don't even have to actually multiply that out because I know that this is exhaustive. Those are all the possibilities that we have. So it's just going to be the difference between 0.64 and added to 0.04 and whatever's left. If we multiply it out, let's see if that really works. 0.2 times 0.8 is 0.16. Right? 0.8 times 0.2 is 0.16. Right? So that's 0.32. And if I add these together, this is going to be 0.68, and 0.32 is going to add up to 1. So we have all the possibilities. Okay? All right. So let's move on a little bit from that. So now let's take a look. And again, this is not always going to be a situation where we're going to have uniform probabilities like this. Let's say that the second question is a bit of an easier question, has only four possible answers, only A through D. Well, that second question, your chances of getting correct would be 0.25 and incorrect would be 0.75. So all these probabilities are going to change, but it's going to work exactly the same way. Okay, so we can calculate some possible outcomes that we have here. Let's talk about this in terms of our let's look at it again in terms of our coin. Actually, let's make this a little bit more complicated. Anybody ever here play a craps table in Atlantic City? Or most people stay away from the craps table, right? Because it's very confusing, isn't it? Right? Okay, let's take a look at the craps table. I don't need this. Cancel. Okay, so let's take a look at a craps table. So when you go to a craps table, you roll a die. What does a die look like? It's a cube, right? And it's got 6 numbers on it. Oh, that was a pretty badly drawn cube. It's got 6 numbers on it, right? You got numbers 1 through 6. What's the probability of throwing a 1? 1 out of 6. 2, 1 out of 6. Every one of those possibilities is exactly the same. The only problem is you don't just throw 1 die, you throw 2 die. Probability of each one of them is 1 out of 6 as well. Okay, so let's see. Next trip that we take to the craps table, you guys ever, if you look at a craps table, I got a picture of one here somewhere. Okay, we're going to test something here. All of this stuff over here is very confusing. Come, don't come, pass, don't pass, stuff like this. The stuff in the center here, those are what they call one-roll bets. They only last for one roll of the die, the next roll of the die. This one down here is 11, 5 and 6, right? Anybody see what it pays off? It pays off 15 to 1, right? That's the highest payoff on the craps table is 15 to 1. Very popular bet. So we're going to test that bet right now. Okay, so it pays off 15 to 1. What's the probability of rolling an 11 on any given row. Let's calculate it. Okay, so doing exactly what we did before, or at least a form of what we did before, there's a lot of different possibilities for getting these different numbers. How many possibilities, if we roll a 1 on the first die, how many different possibilities do we have for the second die? Yeah, we could get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4. There's 6, right? 6 possibilities, right? How many possibilities, if we roll a 2 on the first die, how many possibilities we have for the second die? 6 again, right? Okay, and 6 and 6 and 6. So the number of possibilities we get, since it's an independent event, 6 times 6, there's 36 ways, 36 possible outcomes that are all equally likely, right? A 1 on the first die, 2 on the first die is equally likely to a 4 or 5 on the first die. Same thing with second. They're all equally likely, right? They're all independent of one another. Okay, so now there's 36 equally likely possible outcomes of the 2 die, right? How many ways are there to get an 11? Okay, yeah. How many ways are there? What do you need on the first die?
6.
You need a 6. Second die, you need a 5. Well, is there another way? We get a 5 on the first die and a 6 on the second. Anybody think of another way? No, right? Okay, so what's the odds? It's 2 out of 36, right? What is 2 out of 36? That's 1 out of 18. How much does it pay off? 15 to 1, right? So let's think about this. What is 1 out of 18? What's the probability of 1 over 18? Somebody with a calculator?
5%.
Right, 5%. Okay, what's 1 out of 15?
6%.
Is it that? No, it's got to be more than that, right? I think that's off.
0.06.
Let's see. Let me think about this for a second. 15 to 1. 15 to 1. 15 to 1 and 18 to 1. Let's see. I'm going to do 1 to 15 to 1 over 18 to 1 is let me think about this for a second. Probability of it coming up is 3 over 18. 3 over 18 is the difference. Oh, I'm sorry. 18 to 1. So you got 2 out of 36 over 1 out of 15. Well, at any rate, I'll figure this out later on. But you're roughly at a 15 to 1. You're roughly at I think a 6 or 7% disadvantage when you play that number. In other words, for every $100 that you play that number, you'll lose $15 over the long term, right? Because the odds of it occurring are 1 to 18, but they're only playing off 15 to 1. 11% difference. It's even more. 1/15 minus 1/18. Yeah, what's the difference? No, that's wrong. We're figuring it the wrong way. Because that would be a pretty good bet if that were the case. It should pay off. Like, in other words, what it should pay off is 18 to 1. So on $100, it should pay $1,800, right? So, but it actually only pays 15 to 1, which is $1,500. So you're $300 over $1,800 short, right? It should pay $1,800. It only pays $1,500, 15 to 1 on a $100 bet, right? So you're $300 out of $1,800 short. So it's 3 over 1,500 is how much of a disadvantage you are. So what is that? That's like 15% or more. Yes. To make a long story short, it's the worst bet on the table. right? And everybody plays it. You ever hear them say yelling yo or something like yo means 11 on the craps table. So it's popular because you look at it, it looks like a great payoff because it's 15 to 1. But in fact, the likelihood of it's coming up, of your winning that, is a much lower percentage than almost any other bet on the craps table. Okay, so if you get a close look at probability, you can start to understand a lot about the relationships between how different events and how they might occur, whether they're exclusive, whether they're independent of one another, and whether or not there's like some hidden traps in them. So I'm going to take a look at the next file that we have.
Just an example. So
yeah,
the odds of you rolling it, you can say are 18 to 1.
Yes.
Or 1 out of 18 instead of. So that's really what it should pay then. It should be. Like
it should be 18 to 1, right? So if you bet $100, it should pay 1,800, right? But in fact, it only pays 1,500, right? 15 to 1. Okay.
It's 17 to 1. Right?
What? No, 18 to 1. You have 2 possibilities out of 36. So the odds of that coming up are 1 out of 18. In other words, if there are 18 possible outcomes, only 1 of them wins. So it's 1 out of 18. Oh no, yeah, you're talking, yeah. Well, I'm talking about the payoff. If you bet $100, you should get $1,800 back, right? Like at the bottom's 100, the top should be 1,800. Okay, you're right. We're going to talk about odds later on, and we'll really confuse you then. Okay, we'll take a break now to avoid confusing you when we can confuse you about that a little later. Okay, so I'm going to take a look at a series of a population, and we're going to look at this in terms of what the odds of certain occurrences in this population are. Okay, so let's take a look at this. Here's a table that represents the marital status. This is a number of years ago, so the population is a lot smaller. The marital status for people that are 18 years or older in the United States, these numbers are in millions. Okay, so now, if I were to ask you, if you were to randomly select a person in this population in the United States at this time, what's the probability that person is going to be divorced? How would you determine that? Well, how many people do you have in total in the United States at that time that are included in this age range? 214 million, right? Okay, so how many people in this population are divorced? Right, so what would you say is the probability that you would, if you randomly select a person, that they're going to be divorced?
Out of 1 and
Well, out of 214 million, we have 22 million that are divorced, so it would be 22 million over 214 million, right? About 10%, right? So it's going to be about 10%. Okay, next question. What's the probability that in this population a person is male? Right? Well, how many people do we have in this population again? 214 million. And how many of them are male? 104. So what's the probability of being male in this population if we randomly select a person?
50%.
A little less than 50%, right? Okay, more females than males in this population. Okay, so now let's take another look at something. What's the probability that a person is both male and a widower in this population? Okay, again, what's the size of the population? 214 million, size of the population. How many of those people are both male and widowed? 2.7. So what's the probability we randomly select a person and they're both male and widowed? 2.7 over 214, right? About 1% or so, right? A little bit more than 1%. Okay, so now let's take a look at another example. Given that a person is male, what's the probability that he's married? I'm going to wait for you to come up with this. You give me the 2 numbers. Given that a person is male, what's the probability that he's married? What's the ratio I need here?
63.5 out of 1.
Okay, male. Okay, out of how much? 63.5 out of? Hang on a second. Given that a person is male, we're not counting the females, right? So we're only interested in the males. We're only interested in the top row. 104, right? So it's going to be 63.5 out of 104. Okay. Notice I said a condition. The condition was given that they were male. right? Given that we satisfied that condition first, what's the probability now that they're married also? What do you think we might call that? We already heard the word. I just said it right now, and you heard it earlier today. What is it? It's a conditional probability, right? And when we move on to diagnostic testing, we're gonna see a great example of a conditional probability. Okay, they're really important to us, conditional probabilities, because a lot of times we put conditions like that on what we're examining. So that is a conditional probability. By the way, what do you think they call this table that we have laid out here? What are we going to be calling this in the future? We're going to be calling this either crosstabs or a contingency table. Okay, it gives us an idea of what the breakdown of possibilities or outcomes and so on and so forth. It's a good way to organize data, right? So a lot better, easier way to organize data and view it than if we had just a list of, people, this person's male and this and so on and so forth.
Is this on Blackboard, by the way, this document?
Yes, yeah, it's on the lab section. Okay, I think it's called, it's just the one that's listed as number 3. Okay, so now let's take a look now at our, let's go back and take a look now at our diagnostic tests. Okay, and I'm gonna, instead of looking at this kind of theoretically, I'm gonna actually come up with an example for us. Okay, so now imagine this. Anybody here have a nickel allergy by any chance? Yeah, how do you know? Piercings or something like that? Or yeah, piercings are getting a lot more popular these days. A lot of times they may have, stainless steel piercings and stainless steel rings and stuff like that. And nickel is one of the components of stainless steel, as well as it's alloyed in a lot of other metals. The backs of watches, stainless steel, have nickel in them and so on and so forth. Nickel allergies are increasing in prevalence in general. So let's say that we wanted a simple test, a simple diagnostic test to see if you're allergic to nickel. Okay, do they still do the challenge test? What is that called? Where they poke you with, what is that? Yes, what is that called, that test? Patch test, right? Do they still do patch tests? Yeah, for allergies, they still do that, right? Okay. Let's say that you want to avoid a patch test, and there's some simpler test that you can give someone, maybe part of a blood test that you can just add or something like that. Let's say we want a diagnostic test for determining whether someone is allergic to nickel, okay? And we have some mechanism where we know that we can say that person for sure is allergic to nickel. So I'm going to take a situation where I'm going to take 100 people. I've developed this test. I want to see how good a test it is, okay? So I'm going to take 100 people that I know are allergic to nickel, and I'm going to try this diagnostic test on them. If the diagnostic test is perfect, I would expect I'll identify 100 people as being allergic to nickel, right? I'll get it right 100% of the time. Let's say that I take those 100 people, I know they're all allergic, but only 80% of them come up as being allergic to nickel, okay? That test is only 80% accurate at identifying people that have a nickel allergy. What are we going to call that? That percentage. We're going to call that the sensitivity of the test. The sensitivity of the test is the probability that you will correctly identify people that actually have the condition. If you got 70 out of 100, it'd be 70% sensitivity. Okay, so now let's say I take 100 people that are not allergic to nickel, right? That 100 people that I know absolutely are not allergic to nickel, we did a challenge test and so on and so forth, and I apply this new diagnostic test. And 90 of them I identify as negative, but 10% of them turn up positive. So I got it wrong 10% of the time, but I got it right 90% of the time. So 90% of the time I correctly identified with this test people who are not allergic, okay? 90% right at identifying people that are not allergic. That's the sensitivity of the test. That's the difference between specificity of the test. Specificity of the test. Right? I hate myself for doing that because just when I think I got you, we're going the right direction. Right? So the sensitivity of the test is how good you are at identifying people that have the disease, right? That you correctly identify as positive people have the disease. The specificity is how good you are at telling them people don't have the disease. In other words, you want the test to be negative, for people that don't have the disease, positive people who do have the disease. Okay, so now we do this test. And when we do this test, we find that our sensitivity is 80% and our specificity is 90%. Okay, so now I'm gonna make up I'm gonna open up a spreadsheet I have here, just an outline of a spreadsheet, just to make things to save a little bit of time. Okay, here we go. Good. Okay, so I have a table here that I've created. Okay, and in the rows are the outcomes of the test, whether it's positive or negative. And in the columns is whether or not the person actually has that condition. D plus means they have the disease or condition, nickel allergy. D minus means that they don't. T plus means that they have, they test positive. T minus means they test negative. Okay, so I'm going to do this for a bunch of people. Now, if a person is in this cell over here, what kind of test is that? Now, I'll give you some choices. True positive, false positive, true negative, false negative. True positive, good work. Okay, good. Now, if a person has the disease but tests negative, what is he? False positive, a little harder, right? False positive, right? He tested, false negative, right? Okay, false negative. He tested negative, but he actually has the disease, so it's a false negative. How about here? He tested positive, right? Is it a true positive or a false positive? False positive. And how about down here? Only one left, right? True negative. Okay, good. That's our layout for this table. So now I'm going to take a population. Okay, I'm going to make up this population. I'm going to say that this population, the prevalence of nickel allergy in this population is 20%. Is maybe I'll make it a little bit different. Maybe make it 15%. Okay, so actually, yeah, let's make it 15%. Okay, so I'm going to say I'm going to randomly select 1,000 people in this population. So there's a total of 1,000 people in this population. If the prevalence is 1,000, how many people have the disease? So the prevalence is 15%. How many people have the disease? 150, right? 15% of the population has the disease, so 150. How many people would be negative in that population? Don't have the disease, don't have the allergy. 850. Okay, everybody comfortable with that? Okay, so now I'm going to say, let's apply our test to this population. Of the 150 people who have the disease, what is the sensitivity of my test again? Anybody remember? It's 80%. So we should get that right 80% of the time. So how many people are going to be in here, are going to be true positives? 120. And how are we going to get that? We're going to get that by 150 times 0.8. Times 0.8, right? Oops, excuse me. 0.8. Okay, 120. How many people did we test? How many people were that? How many people have the disease tested negative? It's going to be 30, right? The difference. Okay, so now let's look at our people that don't have the disease. How many of those people are going to test negative? Well, what do I need to know to determine that? I need to know how good the test is at identifying people that are negative. What do we call that again? Specificity. What was the specificity? 90%. It's a little bit better than sensitivity. So 90% of these test negative. So that's going to be equal to 850 times 0.9, right? What's that come out to? 765. So how many people do we wind up getting wrong and test positive? What's that? The difference. Okay, difference is good. I like difference. 850 minus 765. Or 10%, right? That's also true, 85. Right, it's 10%, obviously 90% right, 10% of the time that we're going to get wrong. Okay, good. How many people in this population of 1,000 tested positive? Yeah, it's the sum of those two, right? 150 and whatever that was, 205, right? How many people tested negative? Yeah. Okay, pretty good, right? Pretty simple so far. Okay, so now let's say you go to the doctor and you say to yourself, you go to the doctor tests you, says, oh, you came up positive for our new nickel allergy test, right? How likely is it that you really are positive? Let's give that a name. If you test positive, how likely are you to be positive? Let's call that the positive predictive value. If you test positive, how good is it that really predicting that you're positive? Okay, so let's take a look at that positive predictive value. Okay. How many people tested positive? 205. How many people out of those 205 people were really positive? 120. So what's the positive predictive value? What's the likelihood? Equals 120 over 205. Right? So what's the positive predictive value? About 59%, right? 41% of the time it's going to be wrong, right? It's not going to be accurate. It's going to be wrong. Okay, so that's our positive predictive value. How about if I want to invent something called a negative predictive value? Okay, what's a negative predictive value with this test? Okay, you test negative. How sure are we that you really are negative? How many people tested negative? 795. And 795 tested negative. How many of them are really negative? Right, so our negative predictive value is better. It's equal to 765. 765 divided by 795. So our negative predictive value is 96%. You test negative, you're 96% certain that you don't have a nickel allergy. But if you test positive, right, well, 59% chance that you have this condition. Not too bad, right? I mean, it's more likely than not that if you test positive, that he got it right, and you can go on and get some expensive treatment, or allergies, start taking allergy shots for the rest of your life, or lose, stop wearing watches, or whatever extreme measure that you have to have. I'm a little bit. The reason why I like using this example, because I developed kind of like from wearing watches and sweating on them, a little bit of a nickel allergy, where I get a rash underneath the watch when I perspire, right? But fortunately, Apple came along, and what did they do? They put glass on the bottom of the watch, so I can wear a watch again. For about 15 years, I haven't been wearing watches. So at any rate, so that's pretty interesting. Let's take a look at this again. We're going to do exactly the same thing, except we're going to look at it and say to ourselves, well, what if you look at it in another population where the prevalence of nickel allergies is only 1% instead of 15%? It's much rarer than it is in this population. Okay, so I'm going to do this. I'm going to go over here, and I'm going to go down here, and I'm going to go back up to our table up here, and I'm going to start filling in numbers there instead. I'm going to use that same 1,000, and I'm going to say, okay. Now the prevalence, that would indicate the number of people have disease if the prevalence is only 1%. Let me put that in here. Prevalence equals 1%. Okay, how many people out of that 1,000 would I expect to have this disease or condition? 10, right? 1% of them. How many people wouldn't have it? 990. Okay, so now there's only 10 people have the disease, 80% sensitivity. How many people would I expect to get it right? True positives. 8, and I would get 2 wrong, right? 2 of them would be wrong. They test negative. Okay, so now among the people who don't have the disease, 990. Right? How many of those are 90% correct, 90% accurate at this test, which is better than the sensitivity? How many out of those 990 would I expect to get wrong? In other words, have false positives, test positive, right? What's that going to be equal to? It's going to be equal to 990 times I'll do it this way. The number of people I would expect to get right is going to be equal to 990 times 0.9, right? 90% of the time I'm going to get it right. So I'm going to get it right for 891 people. How many people am I going to get it wrong for? The difference, right? What's that going to be? 99, 1%, right? Which we could have seen anyway. Okay, so how many people in this population tested positive? Okay, how many people tested negative? 393. Okay, so now let's calculate our positive predictive value now. What's it going to be equal to? Let me get this a little wider here. Equals, how many? 8? 8 over 107. What's our positive predictive value now? 7%. That hurts, right? Now, if it's an important test, let's pick another disease that is not, that's a relatively low prevalence in the population that is popular to test for. Okay, so let's say uterine cancers, right? They do pap smears and stuff like that, right? Right. So pap smears have a given sensitivity and specificity, but now I'm going to do negative predictive value first. So we just can take a look at that and see what that is, and that's actually going to be pretty good, right? It's going to be pretty high. You see that because I don't have the decimal points that I want. So we get it now. Oops, still not good enough. Well, you can see it's better. It's better than 99%. Let me go ahead and do that. Let's give it another decimal place. So you can see it's not actually 100. Okay, so negative predictive value gets very good when the prevalence is low, but the positive predictive value really deteriorates, right? Okay, why is that occurring? It's occurring because we're applying the test to many people that don't have the disease. So that means we're going to get more and more false positives, right? So what does that mean? That means that a test like a pap smear, you're going to get a lot of false positives, which means that people are going to go on for more invasive procedures and so on and so forth. There's a lot of controversy over PSAs because they don't have a really good positive predictive value to begin with, and they like to give it to all men over a certain age. So you're testing a lot of people with a prevalence that's not all that high. So you're going to wind up having people go for a lot more invasive procedures because they think they're positive. They have prostate cancer and so on and so forth. So there's a number of these tests that you have to balance you have to make a judgment as to whether the predictive value is good enough for you to say that we should spend more money or do more invasive testing and so on and so forth, or even treatments and so on. Right? So that's pretty interesting, right? This negative predictive value changes not because did the test change. The specificity, sensitivity of the test was exactly the same. The only thing that changed was the prevalence of the disease in the population. Remember, Levi was just talking about how sensitivity and specificity are innate to the test, right? They're part of the test. They don't change, right? But prevalence is not innate to the test. That can change. The results can change based on what happens. But the specificity, and it doesn't matter if you apply this test to a population that has a prevalence of 1% or a prevalence of 80%. The sensitivity and the specificity is always going to be the same. It's always going to be just as good at identifying positive and negatives, but the fact that the prevalence is low is going to affect the predictive value of the test. Okay, so let's take a look at this predictive value. What kind of thing is this predictive value? Can I apply another name to this that we've discussed tonight? Let me put it, I'm going to phrase it another way. Given that you test positive, what's the likelihood that you have the disease? What does that sound like? It's conditional probability. Positive predictive value is a classic example of a conditional probability. Okay, so now what we can do now is that we can apply Bayes' theorem. Now, there's a couple of ways I could do this. One way is to like really torture you, and with this, or I can like simplify. I can come up with a formula that kind of represents it. Let me see if I can blow this formula up. Okay, so I'm going to blow this up so we can see it. Let me move this thing out of the way. By the way, how are you guys doing online? Any questions online? I don't see any questions. I see you've been, okay, good, thank you. I see you've been answering a lot of the questions as we go along, but I want to make sure. Okay, I want to get this big enough to fit in here, but still big enough for us to see the whole thing. Okay, let's take a look at this. This is an example of a conditional probability, positive predictive value. What do I have to know to complete this, to calculate the positive predictive value? I need to know, what do you see there? Sensitivity, prevalence, and specificity. That's the only thing in that formula, right? Okay, so let's take a look at what this really is here. So typically when we calculated a probability before, we made a ratio up. We had a ratio at the top, was in the numerator was the number of ways that we could get an outcome that we were looking for, right? Like the number of heads, over the total number of possibilities. Like with a die, the number of ways we could get 11 over the total number of ways we could get other numbers, total number of outcomes we could possibly have. So let's see how this applies here. Okay, so the sensitivity times the prevalence, right? The prevalence, the disease, if the disease is 10% in the population, and you're going to get you're going to get 80% of the time, sensitivity 80% of the time, you're going to identify those 10% correctly, right? 20% of the time you're going to get it wrong. 80% times 10% leaves you with 8%. So 8% of the population are the number of people that are going to test positive when you apply that test, right? That's the number of people that are going to test positive that actually have the disease, right? Because they're inside that the prevalence 10%. That's the portion of the population that has the disease. So if 10% of the population it has a disease, and you're going to get it right 80% of the time, 8% of the outcomes are going to be those people that have the disease and tested positive. Okay, so let's look down here. Okay, the sensitivity times the prevalence. Okay, now what does that represent? That represents, let's see, the prevalence is 10% and the sensitivity is 90%. So those are the number of people that are going to test. Remember, the prevalence is the people that have the disease. Sensitivity is 90%. So 90% of the time, you're going to, let's see, let me think about this a second. Prevalence is the people that have the disease. So these are the people, let's see, 10% of the population times 90% of the time, you're, what's that? Sensitivity.
Yeah, that's what you specificity.
No, that's just right. It's sensitivity.
So I think we were using 8.8.
Oh.
Right?
It's the sensitivity was 0.8. Okay. This is 0.9. Sensitivity, I'm sorry. What am I thinking? Yeah, I'm off on a tangent. I was reading sensitivity, and in my head was specificity. The sensitivity is 80%, and the prevalence is 10%. So up here, we have the number of people that are correctly identified. 8% is correctly identified as having the disease. They're true positives, right? And down here are our true positives, right? Sensitivity times our prevalence is true positives up here. 8% of the time, we'll get it right. Okay, 8% of the time we'll identify 8% of the people have the disease and test positive, and 8% of the time here they'll have the disease and test positive, right? So what are the other people that we're missing on the bottom here? They're the people that tested positive that don't have the disease. Okay, so what are we looking for here for positive predictive value? The number of people that test positive and have the disease over the total number of people that test positive. Isn't that how we did that before? Right? Wasn't that what this was? Positive predictive value was 8 over 107. The number of people, the percentage or number of people that test positive and have the disease over the total number of people that test positive. Okay, right? Isn't that what I'm doing in this formula also? Or I'm about to do in this formula? 8% of the time, 8% of the population will be true positives. We'll have the disease and test positive. That's our 8% down. It's the same 8% down here. but I'm going to get more people testing positive that don't have the disease. How am I going to calculate what they are? Well, 1 minus the prevalence, well, that represents what percentage of the population, right? If we said the prevalence was, what I said prevalence was 10%, right? So that's going to be 90% of the population, right, don't have the disease, 1 minus the prevalence. These are the people that don't have the disease, right? So they don't have the disease. Well, if I multiply that by the specificity, I'll get the true negatives, right? In other words, the specificity is 90% times 90% is going to give me the percentage of the population that tests true negative. But the difference between the 90% and 10% is the percentage of people that don't have the disease that tests positive, right? So 1 minus that is 10% times 90% of the population that should have tested negative. These are the false positives. So these are our true positives. These are our false positives. So what do I wind up for the positive predictive value? I wind up with the percentage of people that are true positives over the percentage of people that are true positives plus false positives. So this is the same thing as when we took our example population and took the number of people that actually have the disease and test positive over the total number of positives. In other words, true positives over true positives plus false positives. Yes?
Can you explain the 1 minus
With some difficulty. Yeah, with some difficulty. I can, yes. Okay. So now let's think about it this way. What percentage of people in this population do not have the disease? Well, the prevalence is 10%. So what percentage? Yeah, so that's where we get that 1 minus. That's the 90% of the population that don't have the disease, right? So they should test negative, right? So now, what percentage of them are we going to get it wrong and think they're positive, right? Well, remember when we were looking at specificity, right? If the specificity was 90%, right? That meant 90% mean 10% of the time we're going to get it wrong. That's that 1 minus of specificity, right? So 90% of the time we get it right. That's how we get the 891. 10% of the time we're going to get it wrong. So that little segment there, 1 minus the specificity is 90% times 1 minus the prevalence, which is 90%. 1 minus specificity is 10%. So 10% of the people that should have been negative, that 1%, 1 minus prevalence, these are all the negatives. 10% of the negatives are going to test positive, but they're not really going to be positive. So these are positives and these are positives. These are true positives. These are false positives, right? So if we work this out, we can use this now to actually calculate the positive predictive value without actually going through this kind of like kludge, this kind of like fake population that I drew here. So let's give it a try for one of these two. Let's give it a try for this one. Okay, so I'm going to work at the top first. So on the top, let's see if I can't do both of these. You know what, I can do two, is I might be able to just drag this into my Excel file here. Let's see. Where did that picture go? Yeah, there we go. Okay, we have the formula handy now. I'm going to move this over here. Good. Okay, so I'm going to work out the top of this. So the top of this is going to be sensitivity times the prevalence. So what is the sensitivity? 0.8 times the prevalence? I think we said 15. I think for this one, I think it's 15, right? Right, didn't we say 15? Yeah, 150, 15 for this one, right? So sensitivity times prevalence is going to be, times 0.15. It's a percentage, right? 0.15. Okay, so 12% of the population is going to test positive, and we're going to get it right. So now let's take a look at the bottom. So we have two numbers we have to resolve here. One is the sensitivity times the prevalence, which is the same thing, right? It's going to be 0.12, right? Okay, so now what about this value here? 1 minus the specificity 1 minus the specificity. Okay, it's going to be equal to 1 minus the specificity. What's that? Specificity 90%, right? 0.9 times 1 minus the prevalence. Prevalence was 15%, so this is 85%, right? Okay, everybody see how I got that? I'm sorry, that's 0.1. Yeah, 0.1. 0.1 times 0.85. Okay, this is the 1 minus the sensitivity, specificity rather, which was 90%, so it's 10%. And this is 1 minus the prevalence, which is 0.85. Okay, so now what is our equation going to wind up being? It's going to be equal to this over the sum of these two numbers. Okay, cross your fingers. What did I get? I got the same answer as I got here. Right? If I stretch this out, bingo, like magic. Right? How many of you didn't think it was going to work? Tell the truth now, right? A couple of you figured out maybe first time around we can't get this right. Now, if I do the same thing up here, let's try the same thing up here. I'm going to bring the formula with me up here. Okay, so top part of this, the sensitivity, the percentage of people that in this population that are going to wind up testing positive with a 1% prevalence. Okay, so this is going to be equal to, sensitivity is the same as before, 0.8, right? That's innate to the test, it doesn't change, times the prevalence, which is 0.01. Okay, good. Okay, so now sensitivity times the prevalence, it's going to be equal to the same thing. Going to be equal to 0.8, right? Sensitivity times the prevalence, 0.01. Okay, and this part's going to be equal to the specificity, which was 90%. 1 minus the specificity is going to be 10%, 0.1, times 1 minus the prevalence. Prevalence was 99, was 1%. This is going to be 0.99. Right? Do I got that right? 0.9 or 0.99? 0.99. Right? Because the prevalence this time is 1%. Right? Didn't we say? Yeah. 0.99. Okay, and what's my positive predictive value going to be equal to? It's going to be equal to the percentage of true positives I'm going to get over the total number of positives. Right? True positives, which are these, and true negative and false positive, which are these. Add them together. Oops, and I messed it up. Hang on a second here. It came out right anyway. I don't know why it didn't like that. So we wound up getting the same answer we got. Okay. All right. So
It is in fact 0.07.
yeah, 7% is our positive predictive value. With this test, 80% sensitivity, 80% sensitivity, 90% specificity. With a 1% prevalence, the probability that you actually have the disease given you test positive is about 7.5% of the time. Okay, so that's how that would work out. Let me see what we got through that pretty quick. Let me see what else I can cover while we're at this. This went unusually quickly. Let me see if there's something back in the lecture that we can review again. Hey, Levi, did you use that version of the lecture that I uploaded, or did you update it? I had uploaded a version of the PowerPoint. Did you use that one? Okay. Almost. Okay. Yeah. Where is it? That's the PowerPoint. Where is that? Let me download it. So maybe what I could do is, how many of you guys having issues with virtual desktop? How about you guys? Anybody else? Anybody else
I
using?
was, and I just bought the software.
You gave up,
I
right?
gave up.
Yeah. Okay. Well, I mean, negative predictive value, we're doing basically the same thing, right? Actually, I'm not even sure. Let me see what let's see if we can invent that ourselves. Okay. First of all, number one, when we look at these different populations that we looked at, how do we calculate now? I'm going to hide this part over here, if I can. Yeah, let's hide this. Okay, so negative predictive value. Let's take our first situation here where the prevalence was 15%, 0.15. Okay, so how do we calculate negative predictive value then? Right? What do we mean by negative predictive value? Phrase it as a conditional probability. Given that, what do you think it would be? Given that a person tests what? Negative. No, hang on. Given that they test negative, what's the probability that they have the disease, right? That they truly are negative, that they don't have the disease, excuse me, right? The negative predictive value is how good it is at identifying people that don't have the disease. So it's just like positive predictive value. Given that you test positive, what's the probability you really have the disease, that you're a true positive, right? So it's the true positives over the true positives plus false positives. That's our negative predictive value, right? So that's our positive predictive value. Our negative predictive value is going to be, given that you test negative, what's the probability that you really are negative, that you don't have the disease? So what's going to be on the top of that equation? The true negatives, right? The number of the people that are truly negative, test negative and are negative, right? What's going to be on the bottom of that equation? It's going to be all of the negatives, the true negatives and the false negatives. Okay, so let's take a look at how we might figure that out. Okay, this is good. I haven't done this before, but why not? We'll fly without a net. Okay, let's see. Let me get my notepad up. Are you after me? Is that what you were after, or were you interested in how we might apply a formula like Bayes' theorem to this?
I figured that you can do it with the positive value, you can do the negative thing as well. But wouldn't the thing be slightly different?
Sure. Let's do it. Let's actually create it. I mean, we could probably go online and find it, but what fun would that be, right? Okay. So now what we want is we want our negative predictive value is going to be the proportion of the population which is true negatives over the true negatives plus the false negatives, right? The real negatives over all the people that tested negative. Okay, so how am I going to get, given the specificity, the sensitivity, sensitivity, and the prevalence, how am I going to get the proportion of people that truly test negative? What's that going to be equal to?
I will need specificity and prevalence.
Yeah, I like that too. Specificity times what?
1
I like that too. 1 minus the prevalence. Right? So we're multiplying the percentage of people that really are negative, right? 1 minus the prevalence, times the specificity, how good we are at predicting that, right? So I'm going to go over here. I'm going to say that I'll come up with new numbers. The specificity is 80%. The sensitivity is 70%, and the prevalence in the population is 10%. Okay? Okay, so what are we going to put that over? We're going to put that over the people that are true negatives, right? So we just repeat that. Specificity times 1 minus prevalence, right? Plus, what are the other outcomes that we need here? We want the false negatives, right? So how do we calculate what the false negatives are? False negatives are people that are positive but tested negative, right? So I need to know how many people in this population are positive. So how many people in this population are positive, right? That's the prevalence, right?
Yeah.
Right? Okay, I'm trying to think of another way to do this. Okay, so now how am I going to know whether a person, the person that tested, that is, let me think of it this way. Person that is positive, right, that tests negative, false negative, is a failure in the sensitivity, right? So I want the sensitivity, 1 minus the sensitivity, right? Sensitivity is 70%. That would be 70% we get it right. 30% of the time, we take people that are positive and we say that they're negative, right? So 1 minus the sensitivity is the percentage of time that I get the positive, that I say positive people are negative, okay? And how many people are positive? That's the prevalence. Okay, so I'm multiplying 1 minus the sensitivity times the prevalence. Okay, does that sound right? The prevalence is 10% of the people are positive, but 30% of the time we get that wrong because the sensitivity is only 70%. Right, so that's where that 1 minus that. So this is the true negatives, and this is the false negatives. People that have the disease that we get wrong because our sensitivity is only 70%. Are you guys happy with that? Let's test that. Let's see if that really works. So the specificity times 1 minus the prevalence. I'm going to get Excel up. I guess the people online are already figuring this out.
Can you use the values in one table?
Well, what I was going to do is I'm going to create a table based on those values so we could check it. That's basically the same thing. Okay. So we'll go back and check it with that. Or if you want, actually, why not? Yeah, let's do it that way. So we can go straight back and check it. Okay, so let's say the specificity was 90%, sensitivity was 80%, and the prevalence was 15%. Right? That's what we had before, right? Okay, so let's figure this out. What's the probability? What percentage of the population are going to be true negatives in this population? What's going to be the specificity times 1 minus prevalence? The specificity is 90%. Times the prevalence is 15%. It's going to be times 0.85. Over, these are going to be our true negatives. I'm going to put that down here too because the true negatives count down here too for the total negatives. Plus 1 minus the sensitivity, which is 80%, which is going to be 0.2, times the percentage of people in the population that actually are positive. 20% of the time we're going to get it wrong and say they're negative, right? So the prevalence is 0.15. Okay, so what is our negative predictive value going to be? It's going to be equal to, let's actually do this. And you people online, keep it down there. They already figured it out. They're ahead of us. Of course, they're at home with a calculator and a beverage and relaxing in bed so that okay, clear. 0.9 times 0.85 is equal to 0.765. Can you tell me if you get something different? 0.765. So this bottom is going to be 0.765 plus, okay, and let's see. Let's see, let me clear this. 0.2 times 0.15. That's equal to 0.03. 0.03 is equal to 0.765 divided by 0.795. Okay, let's see what we get. 0.765 divided by 0.795. Now you would tell me if I got that wrong, right? If I did the math wrong. So I get 99.2. 0.992. Okay, let's see what we got before. And we'll go back and figure out why we got it wrong now. Did we calculate it? Oh, we got 0.9. We didn't get the same thing. Did I do the same thing? 15% prevalence, right? Sensitivity was 80%. And the specificity was 90%. Did I make a mistake there?
It's right.
0.9. Sensitivity was at 0.9. Is it the same?
Yes, 0.765 out of 0.795. That's it. The figure is 10 in the 3.
Oh, I did. I made a mistake here, right? Calculating the point. It's not 0.992. Yeah, what is it? I didn't clear out my calculator is what I did. So I got that. I didn't clear it out. 0.765 divided by 0.795 is equal to 0.962, which is the same thing that we got here. 962. Worked. Good idea. So actually, tell you the truth, that's the first time we've actually sat here and worked it out in class together for one of these predictive values. But cool. Okay, that's a little bit better understanding, I think, than we've had in the past of this stuff. Any questions? I like to end on a success. So what do you say we call it a night since